Check the class. Check the class. Don't internet. Okay. Così a volte non così. Così a me. Two people don't know. Three don't know. Okay, so guys, we are starting now. We are starting. I want to believe that the network is better. The technical issue has been dealt with. So we're going to get started now. Okay. Please join us. Join us. Okay. So please join us. Join us. We are starting the class now. Join us. You can share the link. Invite your friends to join the class. Okay. So I have started. I have started. So you see that under state theory, we'll be looking at definition of sets, types of sets, relationship between sets, Venn diagram, and then applications to past questions. Please, if you have any issues, you can, type on the comment section so we can attend to you properly. Now let's begin with what a set is. Now I'm not going to be writing much, but then I'll just say it, then you watch it, you can write it down in your book. I want to begin by saying that a set is a collection of well-defined objects. A set is a collection of well-defined objects. Okay? So we say that sets are denoted by capital letters. For instance, this is a set A, which is denoted by capital letter. And a set is, the elements of a set are always in small letter, separated by commas, enclosed with a curly bracket. So for instance, this is a set with a capital letter. This is a curly bracket. And the elements of the set are always in small letters, say A, B, C, D. And each of them is separated by a comma. So that is what a set is. Okay? Please note what is that set is enclosed by a curly bracket. If you don't call it curly bracket, you call it a brace. So that is the bracket that is used for sets. All right. Now, sets are represented in two different forms. That is talking about forms in which sets can be represented. It can be in listed form. Sets can also be represented in set builders form. For instance, if I have a set A to be equal to 1, 2, 3, 4, 5, 6, the elements of this set are listed out for us to see. So at this point, we say that this set is in listed form or roster form or tabular form. But if I say that set B is a set of natural numbers, set of natural numbers less than 10. At this point, this set is in set builder's form. Now, what do? You have to transform this set from set builder's form to listed form by listing the elements of this set. And then, how do we do that? We now say that B is a set of, remember, it's a natural number. What are natural numbers? In a very simple term, natural numbers, natural numbers Natural numbers are positive numbers. So let me say that natural numbers are positive numbers, and natural numbers begins from 1. So if I want to list the element of this set, say natural numbers less than 10. That means I'm going to start from 1 and end at 9 because I said less than 10. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So at this point, I have been able to transform this set from set builder's form to listed form before I can make use of it. So that's just the difference. Remember, I said that sets can be represented in two forms, listed form and set builder's form. So in listed form, the elements of the set are listed. But in set builder form, the elements of the set are not listed, but with the properties to which they can be listed. At this point, we say that this is a set of natural numbers less than 10, meaning that the set, the element of this set will start from 1 and end at 9. That is exactly what we are saying. So quickly, we want to look at types of sets, the types of sets that we have. So I'm just going to list them and then explain them for us. Types of sets. Number one, types of sets. Number one, we have empty sets, singleton sets. Number three, we have finite and infinite sets. Number four, we have disjoint sets. Number five, we have equal and equivalent sets. Number six, we have subsets and supersets. Number seven, we have power sets. We have universal sets. Universal set. But there's also a set, okay, let me call it cardinality. Cardinality of sets. So I am going to explain of sets briefly. Okay, so I'm going to, you know, explain this type of set very, very briefly. Don't forget that the questions is that we get to the point where we start solving past questions. But before we reach there, we need to get the understanding. Okay, so empty set, very simple, as the name implies, empty. It means that it is a set that has no elements. So an empty set is a set that has no elements. For instance, mathematically, if you see something like this, that is an empty set, or this, which is a Greek letter for 5. So when you say empty set, there is no element inside this set, so that's an empty set. So you use a brace or a curly bracket to represent an empty set, or you use a 5 to represent an empty set. But don't forget that this is not an empty set. At this point, there's an element inside this set. So you cannot say that this is an empty set. So either you use a curly bracket or you use 5 to represent an empty set. That is that about an empty set. So what do I mean? That when you get empty set, it is a set that has no elements. It's as simple as that. Number 2, singleton set. So if I have a set saying this, set A, which is equals to, now you notice that there is only one element inside this set. So at this point, we call this a singleton set. What is a singleton set? A set that has only one element. That's a singleton set. Okay. Next, we have finite and infinite sets. If I have a set A to be 1, 2, 3, 4, 5, and then I have a set B to be 1, 2, 3, 4, 5, dot, dot, dot. Now, the difference between these two sets is that set A is a finite set, set B is an infinite set. So the question is, what makes a set finite and what makes a set infinite? If the number of elements of a set is countable, it is a finite set. For instance, 1, 2, 3, 4, 5. There are 5 elements in this set. So this is a finite set. But if you look at set B, we have 1, 2, 3, 4, 5, dot, 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 which means the element of the set continues till infinity. It doesn't have an end. Therefore, we say that this is an infinite set. So a set is infinite if the number of elements is not countable. Whereas it is finite if the number of elements is countable. That's the difference between finite and infinite sets. Okay. Now let's look at this joint set. If I have a set A to be 1, 2, 3, 4, 5, and I have a set B to be maybe 6, 7, 8, 9. If you look at set A and set B, you will see that no element of set A is found in set B. Neither is any element of set B found in set A. So at this point, we say that these two sets A and B are disjoint. So now the question is, what do we mean by disjoint sets? We now say that two sets A and B are disjoint if they have no elements in common. Don't forget, the numbers inside are called elements or members of the set. So when sets have no elements in common, we call them disjoint sets. And as we proceed in our studies, we discover that the intersection of two disjoint sets is always an empty set. All right. So the conclusion is that two sets are disjoint if they have no elements in common. And let's look at equal and equivalent sets. So if I have a set A to be 1, 2, 4, 5, and I have set B to be 4, 2, 1, 5, for instance. Please, as far as set is concerned, there is no difference between these two sets A and B. Reason, the elements in set A are also contained in set B. And of course, in set, the order of arrangement does not matter. So, this set A and B are actually equal because the element of state A are also contained in B, and the element of state B are all contained in A. So automatically, state A and state B are equal. So what do we say is an equal state? Two states A and B are equal if they have the same elements. You can say I have one here, I have one, I have two, I have two, I have four, I have four, I have five, I have five. So they contain the same element. We now say that state A and B are equal. Mathematically, we say state A is equal to state B. So two states are equal if they have the same elements. Now, what do we mean by equivalent states? Let's say I have a state A to B, 1, 2, 3, 4. I have state B to be 5, 6, 7, 8. These two states A and B are equivalent. What do we mean when we say they are equivalent? Okay, I'll pause and talk about cardinality of states. Now, if I have a state, say C to be equals to 1, 5, 7, 8. Question is, what is the number of elements in state C? Let's count. 1, 2, 3, 4. There are 4 elements in set C. Therefore, we say that the number of elements in set C is 4. So mathematically, cardinality of a set simply means the number of elements in a set. So instead of saying what is the number of elements in set C, I can say what is the cardinality of set C. So cardinality simply means the number of elements in a set. Now, if I have a set C to be equals to 1, 5, 7, 8, the cardinality of set C reaching as number of elements in set C is equals to 4. Let's count 1, 2, 3, 4. That's what we mean by cardinality of a set. The number of elements in a set. That is cardinality. So, look at set A. Well, now we want to go back to equivalent sets. So look at set A. There are 1, 2, 3, 4, 4 elements, which means that the cardinality of set A is 4, and the cardinality of set B is 1, 2, 3, 4, also 4. So since these two sets have the same cardinality, we say they are equivalent. So when do we say that two sets are equivalent? Two sets are equivalent if they have the same cardinality, meaning A is equivalent to state B. Please note the difference. But I hope you know that this set here can also be called, okay, A and B are equal because they have the same number of elements, the same number, same element, same element. But this one, they are equivalent because they have the same cardinality. So these sets are equal and they can also be equivalent. Why do we say they are also equivalent? Because they can also have the same cardinality. 1, 2, 3, 4. 1, 2, 3, 4. So a set can be both equal and equivalent. I don't want to go much on that, but let's note the difference. In a nutshell, equals and equivalent. Two sets are said to be equal if they have the same or same members, whereas equivalent if they have the same cardinality. I hope that point is clear. Now let's look at subset and superset. Subset and superset. So let's say I have a set A to be equals to 1, 2, 3, 4. And I have set B to be 2 and 3. Now you will agree with me that the elements of set B are gotten from set A. I have 1, 2, 3, 4. I'll just pick 2 and 3 to form another set B. So the elements of set B are gotten from set A, which means that set A gave set B. So since state B came from state A, we now say that B is a subset of state A. So when we talk about subset, we're talking about a set that is derived or gotten from another set. So state B is gotten from state A. Therefore, we now say that B is a subset of state A. Mathematically written as B is a subset of state A, just an elongated C, which is a symbol for subset. Then, since B is a subset of state A, automatically A is the superset of state B. Superset of state B. So that means that A is the superset, the reverse now, the superset of state B. It's as simple as that. So when we say subset, talk about a state that is gotten or derived from another state. That is what subset and superset is all about. Now, I want to quickly talk about power sets. Power sets. But I want to use the concept of subsets to explain power sets so that it will be understandable. Now, let's say I have a set A to be equals to 2 and 4. Now, the elements of set A are just 2 and 4. Now, the simple question is, how many subsets can I derive from state A? Don't forget, the cardinality of state A is 2, 1, 2. Meaning that cardinality, that is the number of elements in state A, is simply 2. That is 1, 2. Now, since the cardinality of state A is just 2, question, how many sets or how many subsets can I derive from state A? Let's see. First, we get 2, that is a set. Next, we have 4. Next thing is 2, 4. Now, is 2, 4 a subset of set A? Yes. So automatically, you have to note that every set is a subset of itself. Meaning that this one gave birth to this one also gave birth to this. That means that these two sets are equal because they have the same element, 2 and 4, 2 and 4. So they are equal. So every set is a subset of itself. That's a point to note. You can even write it down. That every set is a subset of itself. This one gave birth to this one gave birth to this. That is, they are two equal sets. So they are subsets of themselves. Which means that this set is also a subset of this. The number two thing you need to note also is that empty set is a subset of every set. Empty set is a subset of every set. So it is important to also note that. So having known that, we now see that since we have a set A, whose cardinality is 2, that is, there are 2 elements. The question is, how many subsets was I able to derive from set A? Let's count. 1, 2, 3, 4. I'm able to obtain 4 subsets from this particular set. Then if I now put it in a curly bracket, this is no longer a set. It is now an element of this particular set now. So this is an element because it is inside a curly bracket. But it is now a collection of all the subsets I derived from this set A. Therefore, power set is simply a collection of all the subsets of a given set. So I had a set A. These are all the subsets of this particular set. Then that becomes the power set of set A. So power set simply talks about a collection of all the subsets of a given set. Now my question is, what is the cardinality of the power set of set A? These are the subsets of this particular set. So this because I'm 1, 2, 3, 4 are now the elements of this set. That means that the cardinality of the power set is 4. 1, 2, 3, 4. Which means that the cardinality, which is the number of elements of the power set of set A, is equals to 4. 1, 2, 3, 4. So which means that if I have a set A whose cardinality is 4, 1, 2, then I am to obtain 4 subsets from that set, which is 1, 2, 3, 4, which forms the cardinality of this power set. Now, question: if I have a set B to be equals to 1, 2, that is A, B, C. Now, what is the cardinality of set B? 1, 2, 3. There are 3. Question: what will be the cardinality of the power set of set B? In other words, how many subsets can I derive from set B? How many subsets? Okay, let's quickly do it. First of all, I'll have A. Next, I'll have B. Next, I'll have C. I pick A, I pick B, I pick C. Then, now I'll combine two. I'll combine A and B. A comma B. Next will be A comma C. A comma B. A comma C. Next will be B comma C. Next will be A B C. A B C. Then next will be an empty set. So put them in a curly bracket. Now let's count the number of sets. 1, 2, 3, 4, 5, 6, 7, 8. I've been able to obtain 8 subsets. 8 subsets from this particular set, which now forms the power set of set B. So now, what is the cardinality of set B? It is 3. 1, 2, 3. Which means the number of elements in set B is 3. Now, what is the cardinality of the power set of set B? 1, 2, 3, 4, 5, 6, 7, 8. That means the cardinality, which is the number of elements in the power set of set B, is equals to 8. So, this is how I want to summarize this. I have a set B which contains 2 elements. How many subsets was I able to derive that forms the power set of this set now? There were 4. 1, 2, 3, 4. Then I now have another set B with 3 elements. 1, 2, 3. How many subsets was I able to generate? 1, 2, 3, 4, 5, 6, 7, 8. Question: given a set, how do I know how many subsets I'm able to derive from that set? I will use the formula B equals to 2 raised to the power n, where n is the cardinality of that particular set. For instance, when I have set A, which contains 2 elements, 1, 2, and I want to form the power set of this set, how many subsets will I get to form the power set? 1, 2, 3, 4. How do I get that 4 now? I'll come here and write this to be 2 raised to the power n is 1, 2. So I'll drop 2 in the place of n. And 2 raised to the power 2 is 4, which is this 4 here, which is 1, 2, 3, 4. 4 subsets I'm able to get. Okay? In the light of that truth, if you look at set B, how many subsets can I derive? That will be 2 raised to the power, let's count 1, 2, 3, raised to the power 3. That will give me 8. 2 raised to the power 3 is 8, which is 1, 2, 3, 4, 5, 6, 7, 8, which is this 8 now, which forms the cardinality of the power set of set B. So, what are we saying in essence? It's very simple. I can ask you a question, or it could be asked. Given a set, maybe B is equal to 1, 3, 4, 5. What is the cardinality of set B? 1, 2, 3, 4. Now the question is, what is the cardinality of the power set of set B? In other words, how many subsets can I derive from set B that will form the elements of the power set? That will be 2 raised to the power 1, 2, 3, 4 raised to the power 4. And 2 raised to the power 4 is 16. It means that I can derive 16 subsets that will form the power set of this set B. That means that if I have, say, 6 elements now, and I ask, what is the power set of the cardinality of the power set of state B? It simply means that will be 2 raised to power 1, 2, 3, 4, 5, 2 raised to power 5, and 2 raised to power 5 will give you 32. It means I will derive 32 subsets from this particular set that will form the cardinality of the power set of state B. So that is that about power sets. Now let's quickly talk about the universal state. When we talk about the universal state, it's simply the model state. The universal state is like the model state or a set of elements that is under discussion. So mathematically, universal state is given as this, or you can use this as a universal state, or simply you most times you will use different, but universal state can be given as this or this. So if I have a universal state u to be equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the universal state. There are 10 elements inside the universal state. I can form so many subsets from this universal state. I can have a set A to be 2, 4, 6, 8, 10. I can have another set B from this same universal set to be 1, 3, 5, 7, 9. I can have set C to be 1, 4, 8, 7, 8, 6, 7. I can generate as many subsets as possible from this set. As a matter of fact, I may ask, if I have a universal set which contains 10 elements, that means that the cardinality of the power set is 10. So if I ask, what is the cardinality of the power set of the universal set? In other words, how many subsets can I derive from this universal set that will form the power set? That will be 2 raised to power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 raised to power 10. And if you point your calculator, 2 raised to power 10 will give you 1024. It means that if I have a set which contains 10 elements, I can generate 1024 subsets from this particular set that will now form the power set of the power set of this universal set. So which means I can generate 1024 subsets from this page. And this is just 1, 2, 3, which I have generated out of 1024. So which means we can still generate 1021 still from this place. So that is that about that. So please, all you do is that you find time, get a textbook, and then go through types of sets and learn more about it. So for now, we'll stop there as far as types of sets is concerned. So the next thing we want to do is we will look at relationship between sets. Please, if you have questions, you can ask on the comment section. Okay, so let's look at relationship. Relationship between sets. Okay, so let's talk about relationship between faith. So one thing about faith as a topic is that faith is full of stories, but then that's not what we really need because we'll not be asking you stories. But definitely you need these stories to understand the solution part of it. So that's why it's as if I'm a little bit fast. But when we get to solving problems, I'm going to slow down. I'm going to slow down. So relationship between faith. Number one, we'll look at intersection of faith. Two, union of faith. Three, complement of faith. Four, okay, let me just include difference of faith. Okay, so quickly, what do we mean by intersection of faith? The symbol for intersection, okay, let's pick the first one. Let me summarize everything. If I have the universal faith to be 1, 2, 3, 4, 5, 6. These are the elements of the universal set. Then I have subsets like A to B, 1, 3, 4. I have another set subset B to B, maybe 1, 4, 5. And then I have subset C to be 1, 5, and 6. Now, let us look at intersection. Intersection, that's the symbol for intersection. So let's take two sets here, A and B, and find the intersection of these two sets, A and B. That means that A intersection B is going to be, now question, this is set A and this is set B, and all of them are the subset of the universal set. So how do we find the intersection of two sets A and B? It is very simple. Look at the two sets and ask yourself what is common in these two sets. You agree with me that one is here, one is here, so I'll pick one. Three is here, but three is not here, so I'll leave it. Four is here, and four is here, so I'll pick four. So intersection of these two sets, A and B, is 1 and 4. One is here, one is here, you pick one. Four is here, four is here, you pick four. So the intersection of these two sets, A and B, is 1 and 4. So intersection of two sets, A and B, is a set of elements that is common to both sets. As you can see, 1 and 4 is common to both sets. So that's how to find intersection of sets. Very simple. That means that B intersection C will be, let's look at B and C. 1 is here, 1 is here, 5 is here, 5 is here. So it's going to be 1 and 5. 1, 5. Okay, so now there's something I said about this joint set. For instance, if I have a set A to be 1, 3, 5, and I have set B to be say 2, 4, 6. Look at set A and set B. You will agree with me that there is no element that is common to both sets. The therefore means that since there is no element that is common, one is here, one is not here, three is here, three is not here, five is here, five is not here. Therefore means that A intersection B is equals to empty sets. So I made mention of this, that the intersection of two disjoint sets, these two sets are disjoint because they have no elements in common. So the intersection of two disjoint sets is an empty set. Now, let's look at union of sets. Union. Grammatically, that is the symbol for union. So given two states A and B, the union of these two states written as A union B is equal to. Now how do we find union? Let's go. One is here, one is here. So I'll pick one. That suggests intersection. Three is here, but three is not in set B. I'll still pick three for as long as it is common to any of the sets. Four is here, I'll pick four, just one. Okay, five is here, but five is not here. For as long as five is found in any of the sets, I'll pick five. So what does union mean? It is a set of elements that is common to set A, like in the case of three, or common to set B, like in the case of five, or common to both states, like in the case of one and four. Another way you can look at union of states is this. Just bring the element of state A and state B together without repeating the elements. Without repeating the elements. That is union of states. So I bring the element of state A and B together without repeating. That means that if I'm looking for A union C, A union C, that will be one. One is here. I'll pick one. Then three is here, but there's no three. I'll have to pick three. I also pick four, since it's common to one of the sets. And then I'll pick six, which is common to one of the sets. So that is union of sets. Union simply is bring the element of the two sets together without repeating the element. That's what we mean by union of sets. Okay, so having said this, we're now going to move further to look at complement of sets and of course difference of sets. So I want to believe that was understood. Let's look at complement. Complement of sets. Now, what do we mean by complement of sets? This is very simple. If I have a set A, the complement of set A written as A complement or A prime. Any of the symbols you see, they mean the same thing, complement of set. A complement or complement of A or A prime, which is complement of set. Now, how do we find complement of set? Please note, you can never talk about complement without making reference to the universal set. It's important. So let me write out the complement set again, which is 1, 2, 3, 4, 5, 6. Now, a complement simply means, okay, let me write out the element of set A first. The elements of set A are 1, 3, and 4. That's the element of set A, 1, 3, and 4. Now, I want to find A complement. Look at it, A prime, which is A complement. For me to get A complement, it simply means go to the universal set, remove all the elements of set A. Whatever is left becomes the complement of set A, which is A complement. How? Look at set A. I have 1. Go to the universal set, remove 1. 3 is there, remove 3. 4 is there, remove 4. Then what is left? I am left with 2, 5, and 6. That forms the element of the complement set. 2, 5, and 6. That is how to find complement of set. So what is complement of set A? Given a set A, the complement of set A are those elements in the universal set, like 2, 5, and 6 that are not in state A, that are not in this state A. So complement set simply means universal minus A is equals to A complement. That is say, go to the universal set, remove all the elements of set A. That gives you the complement of set A. Okay, with that understanding, let us find B complement. What are the elements of B? They are 1, 4, and 5. 1, 4, and 5. So go to the universal set, remove 1, 4, and 5. You will left with 2, 3, and 6. 2, 3, and 6. That gives you the complement of set B. That is how to find the complement of set. It's as simple as that. Okay? So lastly, we look at difference of state. Of course, difference of state is just similar to complement of state. But just that in complement, you must make reference to the universal state. But in difference of state, it is between two states. So let me use A and B. State A, for instance, the elements of state A are 1, 3, and 4. 1, 3, and 4. The elements of state B are 1, 4, 5. 1, 4, 5. Then the difference of these two sets, A and B, mathematically written as A minus B, or you see something like A slash B. When you see A minus B or A slash B, it simply means difference. So this is A difference B, or actually A slash B, which also means A difference B. So A difference B is simply, what does it mean? It simply means, like we did in complement set, go to set A, remove all the elements of state B. That gives you A difference B. So let's go. I am in A. In B, I have 1. Go there, remove 1. I have 4. Go there and remove 4. There is 5, but there is no 5. So 1 and 4 is A. I go to A and remove 1 and 4. I'm left with 3. That means A difference B is simply 3, which is a singleton set, a set with only one element. Okay, now what will be B difference A? B difference A, of course, this one now means go to B, look at B now, and remove all the elements of set A. So I am in B, I'll remove 1 is in A, I'll remove 1, 4, I'll remove 4, I'm left with 5. That is 5. So when you are looking for complement of a set, go to that set, remove all the elements that are common in the other set. For instance, A difference B means go to A, remove the element of set B. I am in A, I'll remove the element of set B. Like 1 is here, I'll remove 1. 4 is here, I'll remove 4. Then what am I left with? 3. That gives us A difference B. That's how to find the difference of sets. So with this, I would say that we are done with the relationship between sets. So next thing we're going to be looking at is the Venn diagram. We are gradually, moving forward so we can get to solving past questions. This last part, which is Venn diagram, we really need it as it will help us in solving past questions. We really need it. So let's talk about the Venn diagram, which was invented by John Venn, a mathematician. So what did John Venn did? He used circles to represent substrates, and he used rectangle to represent the universal state. So this is a circle which represents the subset of a particular set, and this rectangle here represents the universal set. So these are the subsets A and B. So what do we do in Venn diagram? In Venn diagram, we are mostly interested in the shaded region. Now the question is, what happens in the shaded region? It is where we have elements. So the shaded region tells us that that is where elements are. So that's exactly what we are going to be doing. And mostly, we use Venn diagram to represent relationship between sets, like the intersection of sets, union of sets, complement of sets, difference of sets. That is what we use, basically use Venn diagram to represent. So now let's get started. Venn diagram. Now let me go back to relationship between states so that it will really help us to understand. If I have a universal state, say 1, 2, 3, 4, 5, and I have subsets A to B, maybe 2, comma 3, and I have state B to be maybe 2 and 5. Okay. First of all, let us find the intersection of these two sets A and B. Let's say I have A intersection B. And already we know what an intersection is, which is a set of elements that is common to both sets. Look at set A and B. 2 is here, 2 is here. So that means that the intersection is 2. Look at it there, 2. If I want to put this in a Venn diagram, I'm going to have this. This is set A, this is set B. This is set A, this is set B. Okay, and that's the universal state. Now, we say that 2 is the element that is common to both set A and set B, which is 2. So that 2 will be here because it is common to both set A and set B. That's intersection, which is here. That means that this region here stands for intersection. As you can see, there's elements there too, things and shape this region. So that's the region, the shaded region that I'm interested in. Now, if I have set A and set B like this, A and B, okay, whereby let's look at the union of these two sets, A and B. A union B will be equal to, remember what union is, that it is a set of elements that is common to either set A or set B or both sets. So let's start from both sets. 2 and 2 is common. Look at it here, 2. Then look at 2, 2, and pick 1. Then 3 is here, 5 is here, 3 is here, 5 is here. That's A union B. But now let's put it in a Venn diagram. Union, look at it. A union B, 2 is common, 2 is common. Look at the 2 here, which is intersection. Then look at set A. What is there? Having touched 2, what is there untouched? That is 3. That means 3 is the element now that belongs to only set A. So that means look at it here, 3. Then in B, 5 is untouched. That means 5 belongs to only set B. Look at the 5 here. So that means that there is element in A, there's element in B, there's also element in the intersection, which means that for union, you will always see that everything will be shaded to show that that is union. Of course, element is element is here, element is here. So this place stands for intersection. When everything is shaded, it stands for union. Now let's go to the Venn diagram proper. Okay. is set A and this is set B. This is set A, this is set B. Then this shaded region, that's the universal set. The shaded region here represents intersection. So that means that this is A intersection B. The shaded region, that's what we're interested in. That's A intersection B. But if I have 1, A, and B, this is A, this is B, and then we shade everything as you can see. That is A union B. That is union. Now, let us look at this shading now. If I have this A and I have B, set A and set B, then I shade only A like this. How do we represent this now? What is this? Now, let's learn something. Don't forget at this point that it is only the element of set A. That is the element here. The element belongs to only set A. There is no element in set B. We are only talking about the element of set A. But we know in the naming, we have to combine both set A and set B. So how do we bring them together in naming? Here's what we do. I have element in set A. So that will be A intersection. I cannot write B because there is no element in B. Now, the elements that are not in B, the question is where are they? That brings us to the concept of difference of set, or rather complement of set. This is what I mean. Let's go through this. Let's find B complement. Look at set B. Look at the universal set. Look at set B. Now, B complement. B complement means go to the universal set, remove the element of set B. So I'll remove 2 and 5, 2 and 5. I will left with 1, 3, and 4. So I have 1, 3, and 4. Now here's my question. Are 1, 3, and 4, are they contained in B? No. No. Rather, 1, 3, and 4 are contained in the universal set 1, 3, and 4, which forms the element of the complement set. But don't forget that 1, 3, and 4 are not in set B. So which means that 1, 3, and 4 that are not in set B are contained in B complement. Meaning that if there is no element in set B, then the elements are in B complement. That would also mean that if I'm looking for A now, the elements that are not in A, question, where would they be? They will be in A complement. That is A complement. Just like the elements that are not in B are in B complement. We have seen that. So now let's go back here. Are there elements in set B? No. Where are the elements? They are in B complement. Those elements that are not in B are in B complement. So now, since there are no elements in B, it means that they are in B complement. So the shaded portion here is A intersection B complement. That means that if I have this, so this is A and this is B, and I shade this point, that is where we have elements. So therefore means that this will be, there is no element in A. Now the elements that are not in A, where are they? They are in A complement. Then intersection B. Of course, there are elements in B. Okay, so the similar thing here, if I have this AB, and then I shade this, so looking at this now, what will we say? Note number one, there are no elements in A, and there are also no elements in B. but the elements are in the universal space outside. So that means the universal space. So since there are no elements in A, that means A complement. That means those elements that are not in A are in A complement. And those ones that are not in B are in B complement. That means this is A complement intersection B complement. Or we can write it as A union B all prime. A complement intersection B complement is the same thing as A union B all complement. That is what we call the Morgan's law of states. So this is exactly how we can represent um, state in Venn diagram, and this is two Venn diagrams. Two Venn diagrams. Okay. So the next thing we want to look at now will be three Venn diagrams. So I don't know if anybody has any question so far. Please put it on the comment section. Oh, maybe you want to. Okay. In one of the questions, someone has asked me to prove that A prime intersection B prime is the same thing as A union B all prime. Well, that's the Morgan's law. We are not proving something right now. But however, if you want to verify that, you can just form sets. For instance, just form a universal set, say 1, 2, 3, 4. Then pick subsets like A, maybe 1 and 3. Then pick B to be maybe 1 and 4, for instance. Then, first of all, find A complement, that is A prime. A complement, which means go to the universal set, remove the elements of state A, like 1 and 3, remove 1 and 3, are left with 2 and 4. Look at it, 2, 4. Then B complement will be go to the universal set, remove the element of state B, 1 and 4, remove 1 and 4, are left with 2 and 3. Look at it, 2 and 3. So find A union B. Okay, let's find the left hand side. A prime intersection B prime. So A prime intersection B prime will be, intersection means the element that is common to both sets. And A prime and B prime, the element that is common is 2. 2 is here, 2 is here. So you just pick 2. That's it. Now let's go to the right hand side. Let's first of all deal with the bracket A union B. So A union B will be equals to, that is bring the element of state A and B together. 1, 3, and 4. You have 1, 3, and 4. Then A union B prime. A union B prime means go to the universal space, remove the element of A union B. That will give you A union B prime. A union B is 1, 3, and 4. Remove 1, 3, and 4. You'll be left with 2. So you can see that A prime intersection B prime was equals to 2. And also A union B prime is also equals to 2. So you can see that A prime intersection B prime is equals to A union B of prime. And that is what we call De Morgan's law in algebraic laws of set, which is not within the scope of Jamb. Okay, so I believe that person has learned something. Someone asks, can A prime union B prime be shown on a Venn diagram? Anything can be shown on a Venn diagram. But please, like I said, we are just following Jamb syllabus. To, um, that is what is obtainable as far as Jamb is concerned. That's what we are dealing with. So let's quickly, because we still have things to do, let's just keep moving forward. Okay. Now, let's quickly summarize three Venn diagrams. So let's talk about three Venn diagram. For three Venn diagram, we have, let's say we have state A, state B, and state C. State A, B, and C. Then I shape this place as a universal state. So you can see that the shaded region here is where A, B, and C cut across, cut this entire set. So you will agree with me that this particular element here is common to set A, B, and C. Hey, this is A intersection B intersection C. But if I have set A, B, and C to be like this, then I shape this. Automatically, you will agree with me that this is going to be A union B union C, which is very simple. Now, if I have A, B, and C, A, B, and C to be, then I now shape this place. You can see that the element of state C is completely out, as you can see here. So the intersection is between A and B. So this is where A and B intersect. It therefore means that, of course, you can see that C is out of it, which means C complements. So that will be A intersection B, A and B intersect here. Then intersection C is out of it, that means C complements. If I have A, B, and C, A, B, and C, and I shape this place, you will agree with me that this is between A and C. This is between A and C. So that means this will be A intersection B is completely out of it. So that will be B complement, then intersection C. That means that if I shape this place, that will be between B and C. A will be completely out. So that will be A prime intersection B intersection C. That's what it will be. That means that if I have something like this, A, B, and C, and I shade this A, B, and C. This one means the element is common to set A only, meaning that B and C are completely out of it. So that is going to be A intersection B complement intersection C complement. Meaning that if I shape only this place, that will mean that it is just going to be A complement intersection B intersection C complement, and so on and so forth. So, in a nutshell, okay, so if I have this A, B, and C, so this is the universal set, and then I shape elements. Okay, I shape this, that is the universal set. This means the elements are in the universal set. There is no element in set A, there is no element in set B, there is no element in set C. So if I want to represent this, that will be A complement intersection B complement intersection C complement, or A union B union C or prime, which is the Morgan's law. So this is exactly what we need to know. And so for please remember the this class was supposed to end by 10 o'clock. So for the remaining maybe 15 to 20 minutes, let's just use it and look at application of this in solving real life problems as it is contained in the past question. Okay, so let's begin another journey now, which is application with past questions. Okay, now this is the application to past question. Quickly, let's have a picture of maybe a classroom, for instance. You look at the classroom, and then let's take, for instance, there are maybe 50 people in a classroom, 50 students. And so you have, so the universal set, that is 50. There are 50 students in a class. And then this is A, this is B, and then there is an instruction. The instruction is that while coming to school or coming to the class, you must have eaten either rice or beans or rice and beans. So this is rice and this is beans. Out of 50 students in the class, that's to say there are 50 students in the class. And then I asked, how many students ate rice? I saw 25 hands. And how many students ate beans? I saw 25 hands. If I add the number of students who ate rice only, which is 25, and the number of students who ate beans only, which is 25, that will give me the total number of students in my class, 50. But if I have a case whereby I ask, how many students ate rice and how many students ate beans? Then I saw how many students ate rice. I saw 25 hands. How many students ate beans? I saw 20 hands. And how many students ate rice and beans? I saw 5 hands. If I add the number that ate rice only, and the number that ate beans only, and the number that ate rice and beans, and I total it 25 plus 5 plus 20, that will give me the total number of students in my class. But if I ask, I have and beans, rice and beans, and then I ask, how many students ate rice? I saw 25 hands. How many students ate beans? I saw maybe 20 hands. Then I ask, how many students ate rice and beans? Okay, let me say 20 ate rice only, 20 ate beans only. How many ate rice and beans? I saw 5 hands. How many students did not eat rice nor beans? And I saw 5 hands. So these are the people that did not eat anything. They leave the class, they are outside the class. But if I am counting the number of students in my class, they are also inclusive, just that they refuse to eat while coming to class. So 20 plus 5, 28 rice only, 5 ate rice and beans, 28 only beans, and 5 did not eat. If I sum it, I will still get the 50 students in my class. But now here is the problem. I have rice, I have beans, and then I ask, how many students, remember there are 50 students in the class, how many students ate rice? And then I saw 25 hands. How many students ate beans? And I saw 30 hands. If you add 25 plus 30, that will give you 55. But I have 50 students in the class. So the problem is that when I ask for a student who ate rice, some people who also ate beans carry their hand. That is to say, their food contain rice and beans. And when I ask how many students ate beans, when these people carry their hand, as people who ate beans, there was also rice contained in their food. That is why this number is increased up to 55 instead of the 50 students I have in the class. So the question is, how do I get to know the number of students who ate rice only? And how do I get to know the number of students who ate beans only? So that I will get my balanced number of students in the class. So here it is. Say 25, that means that it is not 25 students who ate rice only, and it is not 30 students who ate beans only. Since I don't know the number that ate rice and beans, I will now assume that X here is the number of students who ate rice and beans. X here represents the number who ate rice and beans. So how do I know the number that ate rice only? Rice only will now be rice minus rice and beans, X. Beans only will be beans minus rice and beans, X. So that means if I add 25 minus X plus X plus 30 minus X, that will give me the total number of students in my class, 50. So now let's do the mathematics now. 25 plus 30 will give me 55. Minus X plus X is 0. Then minus X, so that is minus X equals to 50. So at this point, I'm going to collect like tens. 55, okay, I have minus X is equals to 50. 55 will move to this side and become minus 55. So that minus X is equal to 50 minus 55 will give us minus 5. Meaning that X will be equal to minus and minus will go. So I have, or you multiply through by negative sign, that will give you 5. It therefore means that 5 students ate rice and beans. So here's the next question that can come. Here's the next question that can come in. The next question can be, how many students ate rice only? That will be 25 minus 5. That's 25 minus 5. That will give us 20. That means 20 students ate rice only. How many students ate beans only? That will be 30 minus 5, which is 25. And then the number of students that ate rice and beans, which we just found, is 5. So you can see that if you sum this together, 40 plus 5 plus 25 will now give us the total number of students in the class. So that is how to get this done. So 10 minutes left before we dismiss the class. Now let's go to the past question and then pick a few questions and solve within the 10 minutes that we have. So in 2010, question number 12. In 2010, Jamb Class question now, 2010, question number 12. It says, in a survey of 50 newspaper readers, 40 read Champion and 30 read Guardian, how many read both? In a survey of 50 newspaper readers, 50 people went to read newspaper, 40 read Champion, and 30 read Guardian. Don't forget, there are 50 people. For example, 40 read Champion and 30 read Guardian. That's about 70 already, which has superseded the number of people that went to read the newspaper. So now the question is, how many read both papers? So in a survey of 50 newspaper readers, the number of people that went to read newspaper, let me call it newspaper, is, okay, the total number of people that went to read the newspaper, we can call it the universal set, 50, which is the total number of people that went to read the newspaper. 40 read Champion. Number that read Champion is 40. 30 read Guardian. Number that read Guardian is 30. How many read both? Number that read Champion and Guardian is one we don't know. We call it X. So now put this in a Venn diagram. This is Champion and this is Guardian. Champion, Guardian. The universal set, that is the total number is 50. Now, they said the number that read Champion is 40. Please, the first thing you must always find is always the intersection. So, number that read Guardian, Champion and Guardian is X. We don't know, which is what we are looking for. We put it here, X. Now, what is the number that read Champion only? Champion will now be 40 minus Champion and Guardian, X. Guardian will be 30 minus Champion and Guardian, X. So if you sum everything, it will give you 50. That is 40 minus X plus X plus 30 minus X, which is equals to 50. Next thing is to add 40 plus 30 is 70. Minus X plus X is 0. Then I go with minus X. Look at the minus X is equals to 50. Collect like terms. So minus X is equals to 50. Plus 70 will move and become minus 70. So minus X is equals to 50 minus 70 is minus 20. So multiply through by negative, that means that X will be equals to 20. So it means that 20 students or 20 people read both Guardian and Champion. And that was option C. Option C in this past question. That was 2010, question number 12. Okay. In 2012, The question is, in a class of 46 students, in a class of 46 students, 22 play football and 26 play volleyball. If three students play both games, how many play neither? And how many students play none of the game? So, here is instruction. There are 46 students in a class. As I said, the universal set is 46. 22 play football. So number that play football is 22. Number that play volleyball is 26. 22 play football and 26 play volleyball. If three students play both games, number that play football and volleyball is 3. And the question is, how many play neither? How many play none of the games? So if you put this in a Venn diagram, this is football, this is volleyball. The total number of students in the class is 46. Number that play football and volleyball is 3. So you put here 3. That's the first thing you must find. Then, how many play football? Football, now F, volleyball. Football will be 22 minus football and volleyball minus 3. Then, volleyball will be 26, which is 26 minus football and volleyball 3. Now, how many play football only? That will be 22 minus 3, which is 19. How many play volleyball only? That will be 26 minus 3, which is 23. So it means that football will played by 19 students only. Volleyball will played by 23 students only. And now the question is, how many play neither? You have how many students in the class? 46 students are in the class. How many students participated in the sports, both football and volleyball? Let's see. Football was 19 plus volleyball was 23. So that will give you 19 plus 23, 20, 30, 42. That means 42 students were involved in the sporting activity. Now, how many students play neither? That is how many play football, did not play, volleyball, did not play. You now ask yourself, how many students were involved in the games? There were 46. So 46 minus the number of students, the number of students that were in the class, which is 46, minus the number that participated in the sport, which is 42. So 46 minus 42 will give you 4. Therefore means that 4 students play none of the games. And that is option G. So I take the last question before it's 10 o'clock for us to dismiss this class. Okay. Let me pick one more interesting question. Okay, let me pick 2009 question number 10. 2009 question number 10. 2009 question number 10. It says if x is a set of n squared plus 1 such that n is a positive integer and n lies between 1 and 5. That's what it means. N is greater than or equals to 1, but less than or equals to 5. Okay? And then y is a set of 5n such that n is positive integer and it lies between 1 and 5 as well. Then you have to find x intersection y. Okay, this is a very interesting question. It says x is a set of n squared plus 1 such that n, now this place from here now to this place further gives you more information about this n here. And so that n is a positive integer. That means it's not negative. We're only interested in the positive numbers. And that n lies between 1 and 5. That means n is greater than or equals to 1. And n is less than or equals to 5. Means that the values of n starts from 1 to 5. So means that n starts from 1, 2, 3, 4, 5. With this, you can now generate the values of state x. That means that state x is equals to, come to this place, n squared plus 1, and substitute these values. Now put 1. 1 squared is 1. 1 plus 1 is 2. Next, put 2. 2 squared is 4. 4 plus 1, 5. Put 3. 3 squared is 9. 9 plus 1, 10. Put 4, the next number. 4 squared is 16. 16 plus 1, 17. Now put 5. 5 squared is 25. 25 plus 1 is 26. Those are the elements of state x. Now for the element of state y, let's go. We say that y is a set of 5n. Then this now gives you further information about this n. And we say n lies from 1 to 5, which is the same thing. 1, 2, 3, 4, 5. So now let's find the values of, the elements of state y. That means come here, start with 1, put 1. 5 times 1 is 5. No. Yeah. Okay. Now let's put 1. 5 times 1 is 5. Put 2. 2. There now. So 5 times 2 is 10. Next, put 3. 3 times 5 is 15. Then put 4. 5 times 4 is 20. Put 5. 5 times 5 is 25. So that will be the element of state y. Now we're looking for x intersection y. So x intersection y will be the element, the set of elements that's common to both states, x and y. So 5 is here, 5 is here, I'll pick 5. 10, 10, I'll put 10. What else is common? 17 is not there, 26 is not there, 20. So the element of x intersection y is simply 5 and 10. These are the set of elements that is common to both states. So that is how to deal with that. And that is option A, 5, 10. Okay, so my viewers, that's where we're going to end the class for today. I'll go through the comment sections. I'm going to take your questions. Don't forget, we'll be back again tomorrow for a fresh topic. I'll let us know in the WhatsApp group. For those of you that are there, if you are not there, try and join us. And you can also, subscribe to my channel if you have not subscribed. Like the videos and then watch, comment, and share with your friends. But please, tomorrow we're going to be dealing with a new topic. And tomorrow being Sunday, we are still going to meet by maybe 9 p.m. tomorrow. We're meeting by 9 p.m. to 11 p.m. want to believe that by then network will be better. So thank you very much for staying up to this time. See you again tomorrow by 9 p.m. You can continue to drop your questions. I'll go through them and I will answer them first tomorrow before we start the new topic. Thank you. And bye for now.